Hello, my name is Jake Grillo, and this is my presentation on concrete and wind turbines, a path to recycling. So to get right into it, first I want to define what's the problem, why recycling is really needed in this realm of the renewable energy industry. So currently there's sort of a blade pileup that's happening right now. At the top of the screen, you can see a picture of a bunch of blades cut into sections and being buried. And this is happening from this picture in a landfill in Wyoming. Last year, about 870 blades were buried just under the ground, hopefully, or probably never to be seen again. And this is becoming sort of a problem because there's going to be around 8,000 more removed each of the next 4 years just in the US alone. So if you think about the US compared to the rest of the world, that means there's going to be a lot of blades in the coming years as more and more turbines get decommissioned after their about 20-year lifespan. And obviously, as we're all engineers, we've been learning blades are built really tough, enough to be able to survive hurricanes or any sort of severe weather. And this kind of creates a post-life decommissioning problem. Um, and yeah, I want to talk about that a little bit. So at the end of life for these blades, when they're ready to come down, there's two big problems that we're running into. And it's pretty simple. It's the size and the weight. Obviously, these things are huge. They can be 120 feet long or 40 meters and weigh many tons. That's just a lot of mass to try and deal with. And obviously, as I said, they're very robust. They can't be crushed, and they're really not, it's not economically feasible to be transporting all of these whole all over the place because that's just so long to be able to go on the interstates or any sort of transportation. So what they are doing is they're using diamond encrusted industrial saw blades to cut it into pieces, usually 3 or more, just because that's more manageable of a bite size that you can then take that blade chunk and do something with it instead. But this is a lot of material, obviously, that we should be using for something useful, I think at least. So the next section I want to talk about is kind of connecting the dots, why concrete and wind turbine blades can go hand in hand so well together. But first, before I get into that, I want to talk about concrete and specifically its CO2 production, because I think this is something that a lot of people don't really know. So cement actually accounts for 5% of all global emissions, and it's actually the most consumed substance on Earth after water, which is kind of crazy to wrap your head around. But if you think about it, the built environment that we're all used to living in, there's so much concrete from foundations of houses to sidewalks. Basically, everywhere you look in some sort of urban society, there's going to be concrete around and lots of it. And producing 1 ton of cement or concrete consumes about 400 pounds of coal, and it generates almost a ton of CO2 for just 1 ton of cement. And so, like, as we've discussed, it's very widely used, but at least I feel like it's not widely understood how much of an environmental impact concrete really causes. And so before I really get into it, I want to just read off this quote by Michelle Simpson. She works for the GE Renewable Energy, or she works for GE Renewable Energy, that division of GE. And she kind of is just addressing the ability for these turbine blades and concrete to go hand in hand so well. And she says, it's a very elegant solution because it addresses several requirements for the cement making process, making it more sustainable from multiple perspectives. And so the multiple perspectives is what I didn't really realize was going to come into play. I kind of thought it was going to be like, okay, you mix it in with concrete and you're done. But it's pretty amazing the amount of different portions of the concrete making process that it can account for. So we need to learn a little bit about concrete production in order to understand where our blades can really come into play. And so, yeah, where can our blades substitute? This little diagram is of the basic building blocks of cement, where Portland cement is at the top. That's what is most common in the cement mixing world. It is very robust and lasts a long time, and these are the main elements that make it up. So limestone is on the bottom left. That's one of the main inputs that when you can heat it up to really high temperatures, about 1500 degrees, with some sort of energy input that's usually coal, you can form calcium oxide and CO2. And so calcium oxide is kind of like a setting agent when the concrete is mixed. That's very important. But the CO2 isn't used for anything, and that's a byproduct. And that's where a bulk of the emissions comes from and why it can be so harmful for the environment. And then we also have sand that turns into silica that's mixed in. And then the other two on the right are clay and just other minerals that are important but less prevalent in the mix. So on the left, there's a picture of some of the shredded portions of a blade. And so there's a lot of different places where the materials that the blades have can be subbed in. The first being energy from biogenic matter, that being like the balsa wood that we've been learning about is inside, and some of the resins. That can add a lot of energy in the kiln, which the kiln is where you like normally would put the limestone and the coal and raise it to really high temperatures to be able to form what you want. But you get to offset some of the coal with this biogenic matter that can just burn in there. And then the blade glass fiber contains silica, and so that can obviously replace some of the sand input. And also the blades contain calcium oxide, which, as I said before, is like a setting agent when mixed to create alite. And so that replaces the limestone in the heating process. And then the metal of the blade, which, or I guess the metal of the whole structure itself with like the tower, can be recycled in other ways, just with normal melting of the metal and reforming into whatever the next life will be. And so this is the cross section of a blade from one of the articles I was reading, one of the reports. And as you can see, here we have the glass fiber. That's going to be what breaks down and is our silica input. And then over here with these red sections, that's where we have the sandwich construction of balsa wood and then also more glass fiber. And so this is like, obviously we're not going to, people don't build the blades without big holes in them and webs, because that would be a lot of material and a lot of weight. So there's a lot of air inside the blades, which is good to understand as well. And so that's just where the different portions come from. So how much does this help? Because obviously recycling is on paper always a really good process. You're like, oh, I can take these glass bottles and make them into something new. But sometimes melting all of the glass and trying to refine it to get it back to what the stock input would be sometimes is pretty tough. So production reductions, using turbine blades in the cement process is actually able, one study found, to cut emissions by 27%, which may not seem like a lot, but when you think of all of the world's cement production and just the sheer amount that is being produced, 27% is a pretty considerable amount. If all of that would be able to be offset with turbine blades, which obviously wouldn't, but it would at least help. And a lot of these startup companies that I've been searching and reading about are stating that they're able to reuse about 90 to 99% of blade material by weight, depending on which recycling process I was finding. And usually about 65% of that blade weight will replace the sand, clay, and other raw materials, and 28% takes over the role of coal with the calcium oxide and heat addition. So that's probably like the balsa wood and resins and things like that. And so just to kind of frame everything up, it's kind of hard sometimes to estimate and judge how big something really is when it's really big. And so I thought talking about the numbers a little bit of per blades would help. And so on the left, there's a picture of just some blade scrap that probably isn't being recycled, but obviously has the potential to be. So 1 7-ton blade, which is pretty standard, I guess, for like the 40-meter blades. And they usually weigh about that much. Relieves 5 tons of coal from heating in the kiln, 2.7 tons of silica, 1.9 tons of limestone, and nearly a ton of other mineral-based raw materials. And you might be doing some quick math in your head and thinking, okay, 7 tons of input, and then 5 plus 2.7 plus 1.9 plus 1 is 10.6 tons. How are we getting more out than what we put in? But a lot of that is coming from like the high poundage of coal that we're being able to relieve. Because if we go back to this building blocks of the cement, where we're introducing all of these items from the blade is happening at the end of the process. So we get to basically skip the calcium oxide production where the CO2 is a byproduct. And then we can, and the same with the silica and other materials, we basically get to input our materials that we have from the blades directly at the end of the process for Portland cement, which can make the process very, very efficient. And so when I was doing some reading on different articles and studies, there was one really good one that came from a university in Ireland, I think out of Cork. And it was titled a comparative life cycle assessment in Ireland of these wind turbine blades. And so this plot, the plot that they came up with has some really good information in it. So I thought I'd just describe what we're seeing a little bit. So there's 3 scenarios that you can see at the bottom, and it helps to understand what each of the scenarios are. So scenario 1 is Ireland is looking at potentially decommissioning their wind turbine blades after like the 20-year window that they normally run, and then chopping them up and shipping them off to Germany, because Germany has some large-scale concrete production plants with some massive kilns that they would be able to use all of the raw material from the blades pretty easily. Scenario 2 is they do the same thing with the recycling that we're talking about, but instead they do it in Ireland, and then they get to skip the shipping. Or scenario 3 is they do what we've been doing for a while now, and is just chopping them up and putting them into landfills. But it's interesting, Ireland also stated that they have a higher price per pound of garbage going into the landfill than a lot of other places around the world. So it was even more worth it for them, as we'll see. And then the y-axis is a bit interesting too. It's titled normalized contribution, and that basically represents the normalized contribution to the damage to the respective categories, each of these 4. So basically a positive number would mean it is damaging it, and a negative number would be it's the opposite of damaging it, which I guess you could say is helping. So human health is the first one, and Germany, or the scenario 1 and scenario 2 are negative. So that means it would potentially help human health. Obviously there would be a lot more or a lot less input of CO2 into the atmosphere, and it wouldn't take up room underground in landfills. Ecosystem equality is basically the same or a little bit different, but scenario 3 with the landfill, obviously you're putting something underground, maybe disrupting an ecosystem in that way. And then you're also, for scenario 1, having to ship these blades really far. So that's not the most efficient either. And then scenario 2 is kind of just net neutral on the ecosystem. Climate change followed pretty closely with human health, which makes sense. And the reason why scenario 1 is less than scenario 2 is because you are producing a lot of CO2 if the transportation is powered by fossil fuels. And then resources, we're losing resources if we just put it in the ground, and we're gaining resources if we are able to recycle these. So that makes sense to me as well. So I think it's beneficial to just look at the overall process now that we understand a little bit more of what's going on. So this is a little roadmap that I was able to come up with. So at the very beginning of the process, obviously the blades are brought down from the hub to ground level, which is kind of a feat that they can get them up so high. So getting them down can be troublesome sometimes. Then they're cut into 3 or more pieces for transportation. Again, that's using like the diamond encrusted industrial saws that we talked about. Then it goes to another place to be shredded into football sized pieces. And usually then there's like a second processing of shredding, that there's another plant that specializes in that they'll ship it to shred it into pebble sized pieces. Then once it's down to that size, it can be mixed into the cement creation process at some sort of kiln place or manufacturing industry. And then finally, the last step is the cement gets poured at location and given new life. And this whole process I was reading can take only a few weeks. as long as there's demand for the concrete. Um, because bringing it down and shredding it really doesn't take all that long. It just takes some time to process the sheer amount of material, and then mixing it in and sending it out. Those industries are pretty good at that as well. So it can really go pretty fast. And so as I was doing some research, I was finding some other fun facts that I thought would be interesting to share. Um, Turbine blades aren't the only large object that you can recycle with this process, which I thought was really interesting. There's some airplane wings that work, boat hulls, some car bumpers, basically anything that has the same build, um, with the balsa wood or the resins and the glass fiber. Anything that is built with that is able to go through the same process. And that's actually pretty cool because like the picture on the left is an old boat that is obviously not running anymore and is just kind of sitting in a forest. And that's been kind of a problem, um, because sometimes it costs more to get rid of a boat or something like this, when you pull it out of the water for the last time than to just leave it somewhere. And so it seems like a much better process to when you pull it out of the water and you are done with it, to be able to instead ship it off and possibly get paid for the material, instead of just letting it rot wherever it is. And this is also, I know, a problem over in Morro Bay with some of the boats that are in the harbor or in the bay that are getting pretty old. It's cheaper for their owners to just keep paying like the yearly price to keep it in the harbor than to get it out and have to deal with it just because of the sheer size of them. So if this recycling industry could start to become a little bit more prevalent with the more and more turbine blades being brought down, then a lot of people would probably be able to use those same processes for these kind of one-off um, pieces of equipment or whatever else they want to use to be able to mix into the cement mixing process and get paid for it. So I thought that was pretty cool. And then obviously, coming full circle, it is possible for recycled blades to end up in the foundation of future wind turbines, which I thought was awesome when I was reading. The blades did their time. Now it's time to support the next generation. And I think the coolest thing about this is this can happen in like a month time frame. Like one of the blades that we see in the back of the picture over there could be brought down, and then in just a few short weeks, it could be cut, shredded, mixed into the process, and then repoured at for a new foundation, in a pretty quick turnaround. And yeah, I just think that's pretty cool that it could support new blades. So that is my presentation. Thank you for listening. And do you have any questions?